Hello again, welcome to another video on our Learn APL with Neural Networks series. In this video I'm going to try to give you an intuitive understanding of what backpropagation is and how we are going to make our networks learn. And I'm going to be forward with you. To me personally, I think this is the hardest part of understanding how neural networks work. And that's just because the formal concepts and the actual maths behind it is a little bit more complicated than for the rest of the neural networks things and concepts and whatever. And that's why if you want to dig really deep, this is probably the place that will take you the most time. But the intuitive ideas and the intuitive understanding is, in my opinion, not so difficult. So it's only if you really want to be very careful about learning all the details that this will give you some trouble. So let me give you my intuitive understanding of what we are going to do. So right in front of you we have a representation of a neural network. And by the way, this is from a video by 3 Blue 1 Brown, which is a YouTube channel that I really enjoyed and that I can highly recommend. And he has a short series on neural networks. You can even see here how neural networks learn, and then this is chapter 2. So I'll leave links for these in the description because these are really helpful. But yeah, so without further ado, this is a representation of a neural network over here, and we can see these lines that represent the connections between the neurons, and in particular these are the weights. And then when we feed something to the network, so something was given as input, we feed forward, so the information traverses forward and something comes out on the right. And in here we can see that if what we were giving the network was this image of a 3, then we would like the network to recognize that image as a 3. So that's why there's that light bulb there is turned on and all of these are turned off. But the network was created randomly in the beginning, so what the network produces is not necessarily what we would like. So we can see here that some light bulbs are really bright, for example the 3 and the 7 and the 8, and then some are off, for example the 5, and then some are dim. And what we need to do is we need to teach the network that it shouldn't produce something like this. It shouldn't produce this type of output. It should be closer to this one. And so what we do is we compare the two with our loss function. That's why there's this question here: what's the cost of this difference? So how bad is it that we got this output when we wanted this one? So what's our cost? What's the loss? And so we compute that value. And then what we want is we want to reduce that value. So we want the loss to be small. And so what we do is we look at this neural network, we look at this huge thing, and we think of it as a single function. So think of the neural network as a function. It receives some input, like functions do, and it produces some output, like functions do. And so what we want to do is we want to find the derivative of the network. So remember, the network is a function, so we can compute its derivative. We want to find the derivative of the network because the derivative will point in the direction of increase of our loss, but we want to decrease. So we compute the derivative, and then what we will do is we will take a look at the values we get, because there's many variables in here, because there's many weights and many biases. So we differentiate the neural network with respect to all of those, and then we get some values, some positive values, some negative values, maybe some zeros. And then what we do is we are going to tweak the weights and the biases just a little bit. So we're going to make small steps, small adjustments, small improvements dictated by the derivative, and those small adjustments will help me reduce the loss just a little bit. And then if I do that repeatedly, what happens is that eventually the loss goes down, hopefully. So that's the main idea. The idea is that we want to compute the derivative so that we know how to make these small adjustments to the weights and to the bias vectors. Now what's slightly cumbersome is the figuring out what the algorithm is and what the formulas are. But I already did that for you so that you don't have to worry about it. And I won't record myself getting to the final formulas. I'll just show them to you. And then again, I can definitely recommend this video over here, so the one I'm looking at, and the next one on the series, which is, you have it over there, it's the what is backpropagation really doing. So these two videos are really important if you want to get a more solid understanding of what is going on, and in particular to understand a little bit better the formulas that I am about to show you. So maybe if you feel like it, and if you have the time, pause this video now, go to the description and watch these videos, and especially the one on backpropagation, so chapter 3. So watch them and then come back. Okay, so I'm assuming that you already watched the videos if you wanted, or not. It's totally optional, but it will increase your understanding of what is going on. So after you've watched them, let me show you the formulas that we need to work with. So don't be scared. I know that sometimes things like this can be intimidating, especially if you don't feel very comfortable with sorry about that. I just wanted to make sure that this was right in our faces. So I'll break this down for you, so don't feel overwhelmed. Let's go line by line. Okay? So what we have here is a recursive definition of some values on the left. So just look at the leftmost column. We can see here that we have this dldx, and notice that x is indexed by n. Yeah? And now notice that in the third line we have dldx again, so dldx, but now x is indexed by n minus I. And also the second line and the fourth line has something indexed by n minus I. So that's what's happening here. And now notice that what do I want to show you? Yeah, exactly. So it's right here. So we have, this is indexed by this is indexed by n, because this is where our recursive definition is going to start. It's going to start with the derivative of the loss function, and these x's here they actually correspond to the x's that we produce in our feed forward operator. So if you recall, that produces a vector x's. That's exactly what's going on here. This xn is the last one, and this x of n minus I is some x in that vector. So those things we know how to compute. These are the intermediate outputs of the network. And so we start by computing this value. This is the seed of our algorithm, of our recursive algorithm, that uses the derivative of the loss function, the output of the network, and our target value. And then it's just a recursive function. We see here that this value over here, the dldb indexed by n minus I, is going to depend on the previous value that used x. And then this is just something that we can compute, because we have this f over here is the activation function, and f prime is the derivative, and we have the derivative of our activation function. And these are just some values. This is one of the intermediate outputs of a network, of a layer. This is its weight matrix, and this is the bias vector. So we just need to do this multiplication over here. And now that we have dldb, then we can update dldx, because if you look at the right, it's just the weight matrix times dldb that we just computed. So we can update dldx for the next iteration, and also dldw is going to depend on dldb once again, and also on the value x with this index. And so what this computes is the LDX is the value that is going backwards, because we notice that we start with n, we start at the end of the network, and then we go backwards because when you do the maths and when you do all of these, when you compute all of these derivatives for the bias vectors and the weight matrices, because again, what you want is to make small adjustments to them, and so you need to find derivatives with respect to them. You need to differentiate the loss with respect to those variables, and that's why you have dLdB and dLdW. And when you find those derivatives, what you want to do is you want to use them to make small adjustments to the matrices and the vectors themselves. So that's why we need dLdB and dLdW, and then dLdX is just a helper variable that is helping you propagate all of the information backwards. And we do this recursive definition so that we can save computations when we are trying to differentiate everything, because we see here that in general we have large networks with many layers, and you could compute all the derivatives separately, but you would just end up reusing or recalculating things. And so the great thing about this backpropagation algorithm is that we are reusing computations, so we are not wasting our computational effort. So yeah, so this is my attempt at giving you a very basic understanding of what we are going to do. We are going to do these small adjustments, and in order to do them, we need to implement this recursive algorithm. So the algorithm itself doesn't need, so we don't need to implement a recursive function, but there's clearly a recursive definition of these values. But of course you can do this in a linear fashion with some loop or whatever you prefer. So this was it for this video. I know this can be a little bit overwhelming, so let that sink in. Maybe watch a couple of videos or read a little bit about it. And then in the next video, we will implement this algorithm. So I will see you there. Bye.